I'm delighted to have you as part of this community. Welcome, welcome, welcome. Hello, YouTube friends. Join us as we unravel the mysteries surrounding forcing mathematics. In the mathematical discipline of set theory, forcing is a technique for proving consistency and independence results. Intuitively, forcing can be thought of as a technique to expand the set theoretical universe B to a larger universe B by introducing a new generic object G. Forcing was first used by Paul Cohen in 1963 to prove the independence of the axiom of choice and the continuum hypothesis from Zermelo Fraenkel set theory. It has been considerably reworked and simplified in the following years, and has since served as a powerful technique both in set theory and in areas of mathematical logic such as recursion theory. Descriptive set theory uses the notions of forcing from both recursion theory and set theory. Forcing has also been used in model theory, but it is common in model theory to define genericity directly without mention of forcing. With the groundwork laid, let's now examine intuition and its connections to our previous discussions. Forcing is usually used to construct an expanded universe that satisfies some desired property. For example, the expanded universe might contain many new real numbers, at least of them, identified with subsets of the set of natural numbers that were not there in the old universe, and thereby violate the continuum hypothesis. In order to intuitively justify such an expansion, it is best to think of the old universe as a model M of the set theory, which is itself a set in the real universe B. By the Winheim-Skolem theorem, M can be chosen to be a bare-bones model that is externally countable, which guarantees that there will be many subsets in V that are not in M. Specifically, there is an ordinal that plays the role of the cardinal in M, but is actually countable in V working in V. It should be easy to find one distinct subset of per each element of M. For simplicity, this family of subsets can be characterized with a single subset X_M. However, in some sense, it may be desirable to construct the expanded model M within M. This would help ensure that M resembles M in certain aspects, such as M being the same as M more generally, that cardinal collapse does not occur, and allow fine control over the properties of M more precisely. Every member of M should be given a non-unique name in M. The name can be thought as an expression in terms of X, just like in a simple field extension, ELK. Every element of L can be expressed in terms of. A major component of forcing is manipulating those names within M, so sometimes it may help to directly think of M as the universe, knowing that the theory of forcing guarantees that M will correspond to an actual model. A subtle point of forcing is that, if X is taken to be an arbitrary missing subset of some set in M, then the M constructed within M may not even be a model. This is because X may encode special information about M that is invisible within M, e.g. the countability of M, and thus prove the existence of sets that are too complex for M to describe. Forcing avoids such problems by requiring the newly introduced set X to be a generic set relative to M. Some statements are forced to hold for any generic X. For example, a generic X is forced to be infinite. Furthermore, any property describable in M of a generic set is forced to hold under some forcing condition. The concept of forcing can be defined within M, and it gives M enough reasoning power to prove that M is indeed a model that satisfies the desired properties. Cohen's original technique, now called ramified forcing, is slightly different from the unramified forcing expounded here. Forcing is also equivalent to the method of Boolean-valued models, which some feel is conceptually more natural and intuitive, but usually much more difficult to apply. As we progress, let's shine a spotlight on the role of the model and examine its intricate interplay within our topic. In order for the above approach to work smoothly, M must in fact be a standard transitive model in V, so that membership and other elementary notions can be handled intuitively in both M and V. A standard transitive model can be obtained from any standard model through the Mostovsky collapse lemma, but the existence of any standard model of ZFC or any variant thereof is in itself a stronger assumption than the consistency of ZFC. To get around this issue, A standard technique is to let M be a standard transitive model of an arbitrary finite subset of ZFC. Any axiomatization of ZFC has at least one axiom schema, and thus an infinite number of axioms, the existence of which is guaranteed by the reflection principle. As the goal of a forcing argument is to prove consistency results, this is enough, since any inconsistency in a theory must manifest with the derivation of a finite length, and thus involve only a finite number of axioms. With our curiosity piqued, let's embark on a dedicated exploration of forcing conditions and forcing posits and its fascinating intricacies. Each forcing condition can be regarded as a finite piece of information regarding the object X are joined to the model. There are many different ways of providing information about an object, which give rise to different forcing notions. A general approach to formalizing forcing notions is to regard forcing conditions as abstract objects with a posit structure. A forcing posit is an ordered triple, where is a proton, and 1 is the largest element. Members of are the forcing conditions or just conditions. The order relation PQ means P is stronger than Q. Intuitively, the smaller condition provides more information, just as the smaller interval provides more information about the number than the interval does. Furthermore, the product must be atomless, meaning that it must satisfy the splitting condition for each P. There are Q, are such that Q, are P, with no S such that SQ, are. In other words, it must be possible to strengthen any forcing condition P in at least two incompatible directions. Intuitively, this is because P is only a finite piece of information, whereas an infinite piece of information is needed to determine X. There are various conventions in use. Some authors require to also be antisymmetric so that the relation is a partial order. Some use the term partial order anyway, conflicting with standard terminology, while some use the term product. The largest element can be dispensed with. The reverse ordering is also used, most notably by Saharan Scheller and his co-authors. As we enter this new phase, let's analyze examples from different angles and evaluate its significance. Let South be any infinite set such as, and let the generic object in question be a new subset XS in Cohen's original formulation of forcing. Each forcing condition is a finite set of sentences, either of the form X or a X, that are self-consistent, i.e. a X and a X for the same value of a do not appear in the same condition. This forcing notion is usually called Cohen forcing. The forcing posit for Cohen forcing can be formally written as fin S2. The finite partial functions from south to $2 a stack of our text under reverse inclusion. Cohen forcing satisfies the splitting condition because given any condition P, one can always find an element S not mentioned in P, and add either the sentence X or a X to P to get two new forcing conditions, incompatible with each other. Another instructive example of a forcing posit is I, where I and I is the collection of Borel subsets of I having non-zero Lebesgue measure. The generic object associated with this forcing posit is a random real number R. It can be shown that R falls in every Borel subset of with measure 1, provided that the Borel subset is described in the original unexpanded universe. This can be formalized with the concept of Borel codes. Each forcing condition can be regarded as a random event with probability equal to its measure. Due to the ready intuition this example can provide, probabilistic language is sometimes used with other divergent forcing posits. In the upcoming section, we'll be dissecting generic filters and exploring its implications in greater detail. Even though each individual forcing condition P cannot fully determine the generic object X, the set G of all true forcing conditions does determine X. In fact, without loss of generality, G is commonly considered to be the generic object R joined to M, so the expanded model is called M. It is usually easy enough to show that the originally desired object X is indeed in the model M. Under this convention, the concept of generic object can be described in a general way. Specifically, the set G should be a generic filter on relative to M. The filter condition means that it makes sense that G is a set of all true forcing conditions, 1G, If PQG, then PG. If PQG, then there exists an RG such that RPQ for G to be generic relative to M, as if DM is a dense subset of that is, for each P, there exists a QD such that QP, then GD. Given that M is a countable model, the existence of a generic filter G follows from the ratio-Sikorsky lemma. In fact, slightly more is true. Given a condition P, one can find a generic filter G such that PG due to the splitting condition on, if G is a filter, then G is dense. If GM, then GM because M is a model of ZFC. For this reason, a generic filter is never in M. With our curiosity piqued, let's embark on a dedicated exploration of P names and interpretations and its fascinating intricacies. Associated with a forcing poset is the clasp of names. A name is a set of the form. A PU is a name and P. Given any filter G on, the interpretation or valuation map from names is given by value G val V GPG V PU. The names are, in fact, an expansion of the universe. Given xv, one defines x to be the name, xy, 1yx. Since 1g, it follows that val x, gx in a sense, x is a name for x that does not depend on the specific choice of g. This also allows defining a name for g without explicitly referring to g. Underlying checker permit pin map. So that E operatornumber underlying operatornumber check P Germid pin G equal G. Let's zoom in on rigorous definitions and understand its implications. The concepts of names, interpretations, and X may be defined by transfinite recursion. With the empty set, 1 the successor ordinal to ordinal, the power set operator, and a limit ordinal, define the following hierarchy. Beginnerline. Operatornum varnothing and avarnothin operatornum alpha plus 1 and amarthal operatornum alpha times amarth operatornum lambda and abika operatornum alpha middle for amdendaline. Then the class of names is defined as the name is an ordinal. The interpretation map and the map XX can similarly be defined with a hierarchical construction. Brace yourself for a captivating discussion on forcing as we explore its nuances and implications. Given a generic filter G, one proceeds as follows. The subclass of names in M is denoted let M evaluum. To reduce the study of the set theory of M to that of M, one works with the forcing language, which is built up like ordinary first-order logic, with membership as the binary relation and all the names as constants. Define Pm, boo. UN to be read as P forces in the model M with posit, where P is a condition, is a formula in the forcing language, and the U's are names, to mean that if G is a generic filter containing P, then M of all U G, value N, G. The special case M is often written as M, or simply M. Such statements are true in M, no matter what G is. What is important is that this external definition of the forcing relation Pm is equivalent to an internal definition within M, defined by transfinite induction, specificity induction over the names on instances of UV and UV, and then by ordinary induction over the complexity of formulae. This has the effect that all the properties of M are really properties of M, and the verification of ZFC in M becomes straightforward. This is usually summarized as the following three key properties: truth, M of all G, value N, G if and only if it is forced by G, that is, for some condition PG, we have PM, U, UN. Definability, the statement PM, U, UN is definable in M coherence, PM, U, UN, QPQM, U, UN. In this segment, we'll be unraveling the complexities of internal definition and exploring its multifaceted nature. There are many different but equivalent ways to define the forcing relation M. In M, one way to simplify the definition is to first define a modified forcing relation of Asher-Mermath that is strictly stronger than M. The modified relation of Asher-Mermath still satisfies the three key properties of forcing, but above Asher-Mermath Pervarthi and above Asher-Mermath Pervarthis are not necessarily equivalent even if the first-order formulae and are equivalent. The unmodified forcing relation can then be defined as a pavashamamarth pavarfif pavashamamarth pernanidvarfi. In fact, Cohen's original concept of forcing is essentially a vashamamarth rather than m. The modified forcing relation of vashamamarth can be defined recursively as follows. 1. Pavashamamarth in v means exists w, kin vich powage pavashamamarth w equal u2. Pavashamamarth in v means exists w, kin vich powage pavashamamarth mitin uv exists w, kin uch powage pavashamamarth mitin v3. Pavashamamarth pernidvarfi means neg exists kapik vashamamarth pervarfi 4. Pavashamamarth pivarfi vipsi means a pavashamamarth pervarfi v pavashamamarth perpsi 5. Pavashamamarth pi exists xervarfitsa means exists uinmamarth pavashamamarth pervarfiu. Other symbols of the forcing language can be defined in terms of these symbols. For example, uv means uv, xx means xx, and so on. Cases 1 and 2 depend on each other and on case 3, but the recursion always refers to names with lesser ranks, so transfinite induction allows the definition to go through. By construction, a vashamamarth and thus m automatically satisfies definability. The proof that a vashamamarth also satisfies truth and coherence is by inductively inspecting each of the 5 cases above. Cases 4 and 5 are trivial thanks to the choice of and as the elementary symbols. Cases 1 and 2 relies only on the assumption that G is a filter, and only case 3 requires G to be a generic filter. Formally, an internal definition of the forcing relation such as the one presented above is actually a transformation of an arbitrary formula x enter another formula pu, un where p and r additional variables. The model M does not explicitly appear in the transformation. Note that within M, um just means u is a name, and indeed one may take this transformation as a syntactic definition of the forcing relation in the universe v of all sets regardless of any countable transitive model. However, if one wants to force over some countable transitive model M, then the latter formula should be interpreted under M, i.e. with all quantifiers ranging only over M, in which case it is equivalent to the external semantic definition of M, described at the top of this section. For any formula x, and there's a theorem T of the theory ZFC, for example conjunction of finite number of axioms such that for any countable transitive model M such that MT and any anomalous partial order M and any generic filter G over M are a n merp M ear, a n mp ear, a n. This the sense under which the forcing relation is indeed definable in M. Let's now turn our gaze towards consistency and explore the fascinating connections it has to offer. The discussion above can be summarized by the fundamental consistency result that, given a forcing posit, we may assume the existence of a generic filter G not belonging to the universe V, such that V is again a set theoretic universe that models ZFC. Furthermore, all truths in V may be reduced to truths in V involving the forcing relation. Both styles, adjoining G to either a countable transitive model M or the whole universe V, are commonly used. Less commonly seen is the approach using the internal definition of forcing, in which no mention of set or class models is made. This was Cohen's original method, and in one elaboration, it becomes the method of Boolean valued analysis. In the upcoming section, we'll be shining a light on Cohen forcing. The simplest non-trivial forcing posit is fin, 2. The finite partial functions from to $2 a stack row text under reverse inclusion. That is, a condition P is essentially two disjoint finite subsets P1 and P1 of, to be thought of as the yes and no parts of with no information provided on values outside the domain of page Q is stronger than P means that QP. In other words, the yes and no parts of Q are supersets of the yes and no parts of P, and in that sense, provide more information. Let G be a generic filter for this posit. If P and Q are both in G, then PQ is a condition because G is a filter. This means that GG is a well-defined partial function from to 2 because any two conditions in G agree on their common domain. In fact, G is a total function. Given n, let Dn Pn is defined. Then Dn is dense. Given any P, if n is not in P's domain, a joiner value for another result is in Dn. A condition PGDN has n in its domain, and since PG, we find that n is defined. Let xg1. Get ready to immerse yourself in the world of the countable chain condition as we examine its impact and relevance. A strong antichain is a subset such that if P, Q are and PQ, then P and Q are incompatible. Written PQ, meaning there is no R in such that RP and RQ in the example on Borel sets. Incompatibility means that PQ has zero measure. In the example on finite partial functions, incompatibility means that PQ is not a function. In other words, P and Q assign different values to some domain input. Satisfies the countable chain condition CCC if and only if every antichain in is countable. The name, which is obviously inappropriate, is a holdover from older terminology. Some mathematicians write CSC for countable antichain condition. It is easy to see that I satisfies the CCC because the measures add up to at most 1. Also, Fini 2 satisfies the CCC, but the proof is more difficult. Given an uncountable subfamily W Fini 2, shrink W to an uncountable subfamily with sets of size at most n, for some n this is uncountable, since otherwise Wn our Wn would be a countable union of countable sets, thus countable. If P for uncountably many P, shrink this to an uncountable subfamily and repeat, getting a finite set i.e. EK, BK and an uncountable family WK of incompatible conditions of size NK such that every is in DOM P for at most countable many PWK. Now pick an arbitrary PWK and pick from WK any Q that is not one of the countably many members that have a domain member in common with page, then PIE, EK, BK and QIE, EK, BK are compatible, so W is not an antichain. In other words, Fini 2 antichains are countable. The importance of antichains in forcing is that for most purposes, dense sets and maximal antichains are equivalent. A maximal antichain is one that cannot be extended to a larger antichain. This means that every element P is compatible with some member of A. The existence of a maximal antichain follows from Zorn's lemma. Given a maximal antichain, let D ipkapek, then D is dense, and GD if and only if G. Conversely, given a dense set D, Zorn's lemma shows that there exists a maximal antichain D, and then GD if and only if G. Assume that satisfies the CCC given X, Y, V, with F, X, Y a function in V. One can approximate F inside V as follows. Let U be a name for F by the definition of V and let P be a condition that forces U to be a function from X to Y. Define a function F, X, E, by. For stackra text for left with D exists kinmouth per left e right. By the definability of forcing, this definition makes sense within V. By the coherence of forcing, a different B must come from an incompatible page by CCC, for is countable. In summary, F is unknown in V as it depends on G, but it is not wildly unknown for a CCC forcing. One can identify a countable set of guesses for what the value of F is at any input, independent of G. This has the following very important consequence. If in V, F is a surjection from one infinite ordinal onto another, then there is a surjection G in V, and consequently, a surjection H in V. In particular, cardinals cannot collapse. The conclusion is that in V, in the next segment, we'll be exploring Eastern forcing and its implications for our subject matter. The exact value of the continuum in the above Cohen model, and variants like Fin 2 for cardinals in general, was worked out by Robert M. Solovay, who also worked out how to violate GCH, the generalized continuum hypothesis, for regular cardinals only, a finite number of times. For example, in the above Cohen model, if CH holds in V, then holds in V, William B. Easton worked out the proper class version of violating the GCH for regular cardinals, basically showing that the known restrictions, monotonicity, Cantor's theorem, and Fnig's theorem, were the only ZFC provable restrictions. See Easton's theorem. Easton's work was notable in that it involved forcing with a proper class of conditions. In general, the method of forcing with a proper class of conditions fails to give a model of ZFC. For example, forcing with fin on 2, where on is the proper class of all ordinals, makes the continuum a proper class. On the other hand, forcing with fin on introduces a countable enumeration of the ordinals. In both cases, the resulting V is visibly not a model of ZFC. At one time, it was thought that more sophisticated forcing would also allow an arbitrary variation in the powers of singular cardinals. However, this has turned out to be a difficult, subtle and even surprising problem, with several more restrictions provable in ZFC and with the forcing models depending on the consistency of various large cardinal properties. Many open problems remain. As we venture forward, let's take a closer look at random reals and its impact on our understanding. Random forcing can be defined as forcing over the set P of all compact subsets of a positive measure, ordered by the relation a smaller set in the context of inclusion is a smaller set in the ordering, and represents a condition with more information. There are two types of important dense sets. 1. For any positive integer n, the set D Lefpin-Poperatornium Fraenkelite is dense, where diamp is the diameter of the set page 2. For any Borel subset B of measure 1, the set DBPP, PB is dense. For any filter G and any pair of elements G, there is QG such that Q. In this ordering, this means that any filter is closed under finite intersection. Therefore, by Cantor's intersection theorem, the intersection of all the elements in any filter is non-empty. If G is a filter intersecting the dense set Dn for any positive integer n, then the filter G contains conditions of arbitrarily small positive diameter. Therefore, the intersection of all conditions from G has diameter 0. But the only non-empty sets of diameter 0 are singletons. So there is exactly one real number Rg such that Rgg. Let B be any Borel set of measure 1. If G intersects dB, then Rgb. However, a generic filter over a countable transitive model M is not in M. The real Rg defined by G is probably not an element of M. One issue with this construction is that if pp, then MP is compact, but from the viewpoint of some larger university M, P can be non-compact and the intersection of all conditions from the generic filter G can then be empty. To fix this, we consider the set CP, PG of topological closures of conditions from G because PP, and because G is closed under finite intersection, Cantor's intersection theorem applies and the intersection of the set Celsius is non-empty. Since diamp and the ground model M inherits a metric from the universe B, the set Celsius has elements of arbitrarily small diameter. Finally, there is exactly one rail that belongs to all members of the set Celsius. The generic filter G can be reconstructed from Rg as GPP, Rgp. If M is a name for Rg, i.e. M vola, Grg, and for B M holds MB is a Borel set of measure 1, then by the truth property of forcing, Pm, B. For some Pg there is a name that satisfies. Vala, Gp. For any generic filter G for that Pm, B. Holds for any condition P. Every Borel set can be non-uniquely built up, starting from intervals with rational endpoints and applying the operations of complement and countable union, a countable number of times. The record of such a construction is called a Borel code. Given a Borel set B in V, one recovers a Borel code, and then applies the same construction sequence in M, getting a Borel set B. It can be proven that one gets the same set independent of the code chosen for B, and that basic properties are preserved. For example, if BC, then BC. If B has measure 0, then B has measure 0. This mapping BB is injective. For any set B such that BM and MB is a Borel set of measure 1, one has RGB. This means that G is an infinite random sequence of Ns from the viewpoint of M, which means that it satisfies all statistical tests from the ground model M. So given G, a random real, one can show that GB in Merub in M. Because of this mutual interdefinability between R and G, one generally writes M for M. A different interpretation of reals in M was provided by Dana Scott. Rational numbers in M have names that correspond to countably many distinct rational values assigned to a maximal antichain of Borel sets. In other words, a certain rational valued function on I. Real numbers in M then correspond to Dedekind cuts of such functions, that is, measurable functions. In the upcoming section, we'll be dissecting Boolean valued models and exploring its intricate connections to our topic. Perhaps more clearly, the method can be explained in terms of Boolean valued models. In these, any statement is assigned a truth value from some complete atomless Boolean algebra rather than just a true-false value. Then an ultrafilter is picked in this Boolean algebra, which assigns values true-false to statements of our theory. The point is that the resulting theory has a model that contains this ultrafilter, which can be understood as a new model obtained by extending the old one with this ultrafilter. By picking a Boolean valued model in an appropriate way, we can get a model that has the desired property. In it, only statements that must be true are forced to be true will be true, in a sense, since it has this extension minimality property. In this chapter, we'll be unraveling the enigma of meta-mathematical explanation and discovering its transformative power. In forcing, we usually seek to show that some sentence is consistent with ZFC or optionally some extension of ZFC. One way to interpret the argument is to assume that ZFC is consistent and then prove that ZFC combined with the new sentence is also consistent. Each condition is a finite piece of information. The idea is that only finite pieces are relevant for consistency, since, by the compactness theorem, a theory is satisfiable if and only if every finite subset of its axioms is satisfiable. Then we can pick an infinite set of consistent conditions to extend our model. Therefore, assuming the consistency of ZFC, we prove the consistency of ZFC extended by this infinite set. Let's now turn our attention to logical explanation and examine its role within the larger context. By Gall's second incompleteness theorem, one cannot prove the consistency of any sufficiently strong formal theory, such as ZFC, using only the axioms of the theory itself, unless the theory is inconsistent. Consequently, mathematicians do not attempt to prove the consistency of ZFC using only the axioms of ZFC, or to prove that ZFCH is consistent for any hypothesis H using only ZFCH. For this reason, the aim of a consistency proof is to prove the consistency of ZFCH relative to the consistency of ZFC. Such problems are known as problems of relative consistency, one of which proves. The general scheme of relative consistency proofs follows. As any proof is finite, it uses only a finite number of axioms. ZFC con ZFCH iterfin TT ZFCTH. For any given proof, ZFC can verify the validity of this proof. This is provable by induction on the length of the proof. ZFC at H ZFCTH. Then resolve. ZFC con ZFCH iterfin TT ZFC ZFCTH. By proving the following, it can be concluded that ZFC con ZFCH iterfin TT ZFC ZFCTH ZFC con TH, which is equivalent to ZFC con ZFCH con ZFC, which gives the core of the relative consistency proof is proving. A ZFC proof of con TH can be constructed for any given finite subset T of the ZFC axioms by ZFC instruments, of course. No universal proof of con TH, of course. In ZFC, it is provable that for any condition P, the set of formulas evaluated by names forced by P is deductively closed. Furthermore, for any ZFC axiom, ZFC proves that this axiom is forced by 1. Then it suffices to prove that there is at least one condition that forces H. In the case of Boolean valued forcing, the procedure is similar, proving that the Boolean value of h is not 0. Another approach uses the reflection theorem. For any given finite set of ZFC axioms, there is a ZFC proof that this set of axioms has a countable transitive model. For any given finite set T of ZFC axioms, there is a finite set T of ZFC axioms such that ZFC proves that if a countable transitive model M satisfies T, then M satisfies T by proving that there is finite set T of ZFC axioms such that if a countable transitive model M satisfies T, then M satisfies the hypothesis H. Then, for any given finite set T of ZFC axioms, ZFC proves con TH. Sometimes in a stronger theory south than ZFC is used for proving con TH. Then we have proof of the consistency of ZFCH relative to the consistency of south. Note that ZFC con ZFL, where ZFL is ZFEL, the axiom of constructibility. I'm here to provide you with the best information, so let me know what else you'd like to learn about.